morning to one and all person here. Last class we have discussed about the basic things about power electronics. So we know what is power electronics, where this power electronics has been applied. Those things we have discussed in the last class. So by the continuation of this, today also we are going to discuss some of the introduction about the power electronics and the basic converters, and what is the use of the basic converters and where this basic converters is applying, and some of the basic converters also we are going to discuss in today's class. So by the continuation of the last class, if you see the power electronics, so there are different converters are available in the power electronic circuit. So you can see here basically there are 4 different converters are there. First is AC to DC converters. So we all know that we are using a AC supply. We are using a AC supply in our home appliances. Mostly we are getting a AC supply as the input from the EB. But in most of the applications, the application is operated with the help of a DC supply. For example, you can see your mobile phone. Mobile phone is charging with the help of the DC supply. So you want to convert the AC supply. It is a must. You want to convert the AC supply to the DC supply. So for that, the AC to DC converter has been used. Then next type of converter is AC to AC converter. So in some of the application we record a variable AC voltage. So we want to convert a constant AC voltage to a variable AC voltage. For converting the constant AC voltage to variable AC voltage, we record a converter. So for that conversion, the AC to AC converter has been used. The third type of converter we are going to study in this power electronics subject is DC to DC converter. So most of the applications we are having we are using a DC supply as the input voltage. So in this purpose, some of the application record variable DC voltage as your input supply. So for producing the variable DC voltage as your input supply for some of the specified applications, so we record this type of converter, that is DC to DC converter. It converts the constant DC supply to variable DC supply. Then one more fourth converter is there, that is DC to AC converter. So here the DC supply is converted as a AC converter. So in this here, DC to AC converter is otherwise called as a inverter. So based on the applications, there are different types of converters are there in this inverter circuit. That is voltage source inverter, current source inverter. Those things we will be discussing detail about in the 5th unit of this power electronics. Okay. Anyway, basically there are 4 different types of converters are available in power electronics. But nowadays, if you see the latest research papers, if you see, means there are different types of converters are there. Based upon the applications, they are generating new different types of converters. So today's class, first we are going to discuss about the first type of converter, AC to DC converter. So basically the AC to DC converter is classified into 2 different types. So first is called as uncontrolled rectifier and second is called as controlled rectifier. So you all know about the uncontrolled rectifier and controlled rectifier. Anyway, you have studied about uncontrolled rectifier in your electronic devices subject. Already you have learned previously about uncontrolled rectifier circuit. So here generally if you see the semiconductor switches, there are 2 different semiconductor switches are there. One set of switches is called as the control switches and another one set of switches is called as the uncontrollable switches. The first set of switch is called as the uncontrollable switches. Uncontrollable switches means example we can see as diode and Zener diode. Mostly with the help of diode, if you are designing a rectifier circuit, means it is called as the uncontrolled rectifier circuit. So in the uncontrolled rectifier circuit, the input fixed AC voltage is converted as a fixed DC voltage. So you won't get a controlled output voltage. Whatever input you are giving as an input, the same input will be converted as a DC. So it is not a controlled thing. So it is called as a uncontrolled rectifier circuit. Then next another one set of circuit we are having, or we are going to learn in this power electronics subject is called as the controlled rectifier switches. So here in the controlled rectifier switches, the input voltage is a fixed voltage and the output voltage you will be getting a variable DC as your required variable DC output voltage. So in this controlled rectifier circuit, you will be using a controlled switches. So I have told you previously, there are two different types of switches: controlled semiconductor switches and uncontrolled semiconductor switches. So say some of the controlled semiconductor switches. So you can see you have learned the basic things: IGBT, then thyristor, then transistor switches. So these all things are controlled semiconductor switches. So for designing the controlled rectifier circuit, we required a controlled semiconductor switches. Okay. So in this AC to DC converter, there are different types of AC to DC converters are there. So here I have classified the AC to DC converter based upon some of the types. So first you can see, based on the input supply, it is classified into two different types. So based on input supply, it is classified into two different types. Means, so we are getting a two different input supply. That is, first is a single phase AC supply and second is a three phase AC supply. So if you are using a single phase AC supply, means it is a single phase controlled rectifier. If you are using a three phase AC supply as an input, means it is a three phase controlled rectifier. Then next, based on quadrant operation, it is again classified into three different types. So it is a one quadrant converter, two quadrant converter and four quadrant converter. One quadrant converter means a device it operates in only one quadrant. Two quadrant converter means it is a device operating two quadrants. So totally we know it is a four quadrants are there. One quadrant means it will be operating in one quadrant. This is first, second and third and fourth quadrant. Okay. So in the fourth quadrant means it will be operating in all those four quadrants. So for example, you can take a one quadrant converter means it is nothing but a single phase half wave controlled rectifier. Two quadrant converter means it is a single phase full wave controlled rectifier. Four quadrant converter means it is one of the converter we are having. It is otherwise called as a dual converter. So it is a dual converter is called as a four quadrant converter. The next, based on the pulses, it is classified into again four different types. So based on the pulses operation, for single phase half wave rectifier we will be having a one pulse. So it is called as a one pulse converter. Then same way single phase full wave converter, we will be converting both the positive pulse and negative pulse also. It is called as a two pulse converter. Then three phase half wave converter, we are converting a three phases half pulse. So it is called as a three pulse converter. In the three phase full converter, we are converting three phase positive pulse and three phase negative pulse. That is called as a six pulse converter. So in the second unit fully we will be discussing about AC to DC converter. So I have told you various different types of AC to DC converter. In this AC to DC converter, the first type of AC to DC converter is a one pulse converter. The one pulse converter is otherwise called as the single quadrant converter. So this single quadrant converter is otherwise called as single phase half wave controlled rectifier with R load. So why it is called a single phase half wave controlled rectifier with R load means here we are converting only the half pulse. Only the half pulse we are going to convert. So it is called a single phase half wave. Only the half pulse is converting. So it is called as the half wave converter. And here we are using a controlled switch. So I have told you there are two different types of switches are there. So here we are using a controlled switch. So it is called as the controlled rectifier. Again there are different types of loads are there. R load, RL load and RLE load. So here we are using a R load. So it is called a single here the rectifier circuit, it is used to convert AC supply to DC supply. Because it is a half wave controlled rectifier, you can able to convert and controlled a half wave pulse. You can't, so you know the input supply is a AC supply, means it is a sinusoidal voltage. You will be having two sets of pulses. One is a half pulse and second is the negative pulse. So here the first positive half pulse will be converted. The negative half pulse will not be converted. So that means for converting both the pulse, we will be using a single phase full wave controlled rectifier. So here it is a single phase half wave controlled rectifier. Only the half pulse will be converted. So this is a circuit diagram for single phase half wave controlled rectifier. So initially we will be giving a transformer. The transformer is used to step down to your record voltage. Your input voltage will be a 230 voltage. It is a constant input voltage we are getting from EB. But your record voltage will be a 12 voltage or 9 voltage. For example, we can see your mobile charger. Your mobile charging voltage is a 9 voltage DC voltage. So you want to convert this 230 voltage to 9 voltage DC voltage. So for getting a 9 voltage, we will be using one transformer. So here the transformer is used to convert 230 voltage to 9 voltage. 230 voltage to 9 voltage AC supply. So this step down voltage is given to the rectifier circuit. In the rectifier circuit, we are having one controlled switches. So okay, now you can see here. So this is the input supply, that is sinusoidal voltage. So you will be having two sets of pulses. One pulse is 0 to pi. Second pulse is pi to 2 pi. So first we are going to apply this 0 to pi voltage. 0 to pi first half cycle voltage. When you are applying this 0 to pi voltage, when you are applying this 0 to pi voltage, means here it will be positive and here it will be negative. So this half cycle will be applied to the rectifier circuit. When this half cycle is applied towards the rectifier circuit, so here we are using a thyristor switch. So thyristor, we know there are two terminals are there and three terminals are there, anode, cathode, and another one terminal is there, that is a gate terminal. So when you give the forward voltage across the anode and cathode and you give the gate voltage then you give the gate voltage, the thyristor T1 switch will be turned on. So by giving this half pulse 0 to pi half pulse across the thyristor switch, the thyristor switch will be turned on. When the thyristor switch is turned on, so one more thing is there. So for turning on the thyristor, you want to give the input supply across anode and cathode. Also you want to give the controlling pulse also. So here the controlling pulse is called as the alpha value. So alpha is otherwise called as a triggering pulse, or it is a controlling pulse we will be using. So if it is alpha is equal to 0 degree, so various alpha value you can give. Alpha 0 degree or alpha 30 degree or alpha 45 degree. The various alpha value you can give. So based upon this triggering pulse, the switch will be turned on. So the first we will give the input supply across anode and cathode. Then we will be giving the alpha value 0 degree or 30 degree or 45 degree, whatever value. If you want to trigger the switch from 0 degree, means you can able to trigger the switch from 0 degree, or from 30 degree, means with small time period you can give the alpha value. So now you can see the output voltage waveform. You can clearly understand. So this is the input voltage, that is 0 to pi and pi to 2 pi and 2 pi to 3 pi. So in the pi to 2 pi you are applying the input forward voltage across the thyristor. When you are applying the forward voltage across the thyristor, means also the device will not turn on. When the device will be turned on? So the device will be turned on. So here, when the alpha value is given as 30 degree, from 30 degree onwards, the device will be turned on. Okay. So same in this input voltage, from 30 degree, the device will be start conducting. So you will get this output voltage in the output. Okay. The next half supply is pi to 2 pi. That is a reverse voltage. When you apply the reverse voltage across this circuit, that means here it will be negative and here it will be positive. When you apply the reverse voltage across the circuit, when you apply the reverse voltage means the thyristor switch will not be turned on. So in this time period, you will not get the output voltage. So here you will have the voltage as 0 in the while the operation of pi to 2 pi. Okay, can understand? Then again you will be applying the next positive half cycle voltage 2 pi to 3 pi. When this 2 pi to 3 pi condition, again the next condition will be there, but here the conduction will be start from 2 pi plus alpha to 3 pi. Okay, so here this is the output voltage. But here we are using only the resistive load. So if you are our main condition is that if you are using a resistive load, the output voltage V0 will be is equal to output current V0. So what the output voltage you got in the V0, what the output voltage you have got, it will be same as the I0. So alpha to pi you will be having the conduction value. Then from pi plus alpha to 2 pi plus alpha, you don't have any conduction value. Then from 2 pi plus alpha to 3 pi, you will again get the conduction voltage. Then the next waveform is the voltage across the thyristor VT1. The voltage across the thyristor VT1. Yeah, the voltage across the thyristor VT1 will be, it is the opposite of the voltage of the V0. You can see the waveform. So it is opposite. So wherever the V0 is conducting, you won't have the output voltage here. Wherever the V0 is not conducting, you will have the voltage across the thyristor VT1. Okay. So this is a diagrammatical representation and this is a graphical representation. Also, you can do the mathematical calculation also here. So you can able to calculate the output voltage. Output voltage VDC is equal to, because it is a half wave rectifier, so you will be having 1 by 2 pi, and the limits will be, it is a half cycle, and the limits it starts from alpha to pi, and then the limits will be from alpha to pi. The input voltage, what is the input voltage? So this is the input voltage. Vs is equal to Vm sin omega t. So Vm sin omega t d omega t. Okay. So if you do the integration means you will get the final output voltage VDC. VDC is equal to Vm by pi 1 plus cos alpha. So this is the final output voltage. You will get in a single phase half wave control rectifier with R load. Here only the half pulse will be controlled. So it is called as a single phase half wave controlled rectifier. So in the next topic we will be discussing about single phase full wave controlled rectifier. In the single phase full wave controlled rectifier, both the half pulse will be controlled. Both the positive and the negative half pulse will be controlled. So it will be called as a single phase full wave controlled rectifier. So about single phase full wave controlled rectifier we can discuss it tomorrow.